I need to describe how that affects the availability of the lone pair, and I need to drop in that term, the availability of the lone pair. So I then can add this increases the availability of the lone pair. So I've got all my key points in there. I've said which one's more basic. I've described that the alkyl group is donating electron density towards the nitrogen. I've dropped in that key term inductive effect, and then I've explained why that shifting around of electrons makes it more basic, because I've made the lone pair more available. So if we think about what's going on, I mean the difference in basicity is pretty small, but we've packed, well, this is just our reference point, so this lone pair is fairly available, it will be donated away towards the hydrogen. But in this, we've packed extra electron density onto the nitrogen, so we've got more negative charge crammed in on one point. The negative charges repel each other, and so they want to get away from each other. You can think of a bit like static electricity, where you pack a load of negative charges onto the Van de Graaff generator. So the Van de Graaff generator is that big metal dome, and when you put your hand on it, your hair stands up, or you get a static shock. What that's doing is cramming loads of electrons onto the big metal dome by using the friction of the rubber belt that goes up and down. And then when you stand near it, if you get your hand near it, you provide a route to Earth, and all the built-up negative charges flow through you. And the reason why they're higher in energy because you've crammed loads of electrons next to each other. Now, this is less dramatic than what's going to be going on over there, but it's still the same principle. So it more readily donates away that lone pair towards an H+. Now, you'd also need to be able to think about why the quaternary ammonium salts or ammonium ions aren't basic. So we've got imagine it's a chloride. Now this is just non-basic. So this doesn't have a lone pair that can be donated away. The lone pair, in terms of what I hate the term dated bond, but in terms of your formal Lewis structures, one of these is a Lewis bond using up the lone pair. So both of these electrons in this bond come from the nitrogen, and so there isn't a lone pair that's available to be donated towards a hydrogen. Okay, so then we're going to look at some of the reactions of amines and kind of the synthesis, so making amines. Now, the thing you learned in the Year 12 topics was that a way you could make an amine would be by taking a halogenoalkane of some sort. So if we want to make, let's say we want to make methylamine, nice and simple. Well, I'd take, for the methyl group, I'd use like chloromethane. And I'd react that with ammonia. Attacks the carbon, breaks the CCl bond. We get we end up with actually an ammonium ion, methyl ammonium chloride, and then you can remove the hydrogen from it. So electron go onto the nitrogen, we form, and hydrochloric acid is a byproduct. Now, the problem with this though is this product's got a lone pair on it, and as we just explored, that lone pair is more able to be donated away than it was in ammonia. And so basically, for the same reason that this was a better base than ammonia, it's also a better nucleophile. And so in here it's acting as a nucleophile. It's donating, it's attacking a carbon or some other atom. It's not taking a hydrogen. I mean, it can act as a base, but that's when it removes a hydrogen from something. So this is a better nucleophile as well as being a better base. And so you're going to have the problem that when you take your ammonia and your chloromethane, you're going to form some of this, and then that's going to react with some chloromethane that's left over in the reaction. So we can donate towards the do another nucleophilic substitution. We go through these multiple steps, but then we end up with this. So this is N dimethylamine. And then, well, this has still got an available lone pair, and so that lone pair could be donated towards the carbon, undergo another nucleophilic substitution, and then we end up with NNN trimethylamine. And then, but this has still got an available lone pair, and that can be donated towards. And what we end up with, that should be an N, not a C again. We end up with tetramethylammonium and our counter-ionic chlorides. We end up with tetramethylammonium chloride. So we have the problem of over-alkylation. We have the problem of over-alkylation. So in reality, this is just not used. This reaction mechanism is simply just, it's not used to make amines, at least not just using simple equivalents of amines and halogen alkanes. You have to use complex protecting things to get it to work. So over-alkylation is a significant drawback of this mechanism, and so in a way of making amines, we overlook that entirely at year 12, and then in year 13 we start to realise, okay, there's a bit of a problem with this, and we're going to see a kind of, let's say, a bit of a fudge on the part of the A-level specification for how we might control over-alkylation, and then we'll look at a real way of actually how we can produce the correct amine that we want.